Now, in addition to FO validity and FO consequence, there is, of course, FO equivalence, which corresponds roughly with the notion of tautological equivalence. And this video is dedicated to seeing how that works and to taking a look at the De Morgan equivalences for the quantifiers. Now, we've already seen that there are conditions under which we can treat quantified sentences as, in some sense, atomic, and we're entitled to do this when they have a main connective outside of the scope of the quantificational symbol. Here's an example of one such. So we have two sentences which are quantified, but our main connective is this sign here, and we have these two sentences we can treat as atomic, which are disjuncts of this connective here. Accordingly, we can use the De Morgan's laws that we saw in an earlier video to turn out the following equivalence. Pushing the negation through, we negate these sentences that we're treating as atomic, something is a cat and everything is a bird, to get nothing is a cat or not something is a cat. Flipping this disjunctive sign, so recall that when the negation pushes past a disjunctive sign, it turns it into a conjunctive sign and vice versa, and then negating this right-hand sentence, everything is a bird. So in circumstances in which we have operators outside of the scope of a quantificational sign, we are entitled to treat those operators as just operating on something like atomic sentences, and so ordinary De Morgan's rules apply. Here's one further example. We already saw the sentence earlier, and its main connective is this sign here, the conditional, and so it's straightforwardly equivalent with any of the following. Not everything is a dog or Sparky is a dog, and that's just by our definition of the conditional. If P then Q is equivalent with not P or Q. Likewise, by contraposition, this is equivalent with if Sparky isn't a dog, then not everything is a dog. So this is likewise equivalent with if everything is a dog, then Sparky is a dog. And all of these work simply because they work using the equivalences for the truth functional operators. So these will actually be tautologically equivalent. As you can see, if you plug any of them into a truth table, treating again any of these quantified sentences like everything is a dog as atomic. But there are further equivalences which are not tautological, and these are the ones we're going to explore in greater detail in this video. So taking our Q from the equivalence of not P or Q and if P then Q, we can straightforwardly see that the following two sentences are equivalent. Here, not P or Q can be found on the right-hand side, and conversely, the if P then Q can be found on the left-hand side. So these two are equivalent, and their equivalence turns on these equivalences up here. But the problem is that they're not tautologically equivalent. We can't just plug these into a truth table and discover their equivalence. So we need some notion that's specially tailored to the quantifiers that allows us to see this equivalence and prove this equivalence whenever we come across it. And that is the notion of first-order equivalence. In order to address this, we need to return to our earlier notion of satisfaction. So recall that non-sentence whiffs like cube X are not true or false because they're not really about anything. But an object can be said to satisfy a whiff if, supposing we name that object, we apply a new constant to it, call it n for name, or you could do c for constant, then the sentence cube n is true. So we're going to go off this notion of satisfaction now to talk about our equivalences for quantified sentences. Now, in order to show what we just stated, namely that everything, if it's an F, is a G, is equivalent with everything is not an F or a G, we have to rely on this notion of satisfaction here, and here's what a proof of this will look like. Take two well-formed formulas that are identical with the subformulas of our quantified sentence, everything if it's an F is a G. If X is a P, then X is a Q, and X isn't a P or it's a Q. Now these are equivalent, but showing that these are equivalent means we have to appeal to our prior notion of satisfaction. So we'll assume the opposite, namely that if P then Q is not equivalent with not P or Q, and we're just going to use this sign to symbolize non-equivalence. From this it follows that one of them must be satisfiable while the other isn't. So in that case there's a substitution of a constant for these variables, which renders one true and the other false. So let's pick a constant. We'll call it c. Then we want to substitute c for the free variable x in the above formulas, which will give us the following sentences. Now, since we assume that these would not be equivalent, it has to happen that these two won't be equivalent either. But we can straightforwardly see now that under any conditions in which c is a p implies c is a q, the right-hand sentence c is not a p or c is a q will also hold, because in fact this is our definition of the conditional sign right here. And so this is false. As a result, our assumption that these are not equivalent does not hold, and therefore this equivalence does hold by indirect proof. More generally, we can say that any two whiffs are equivalent just in case they're satisfiable under the same conditions. That is to say, in every possible circumstance, they're both satisfied or not satisfied. Hence, P and Q are logically equivalent well-formed formulas if and only if, in any possible circumstance, whatever objects satisfy P also satisfy Q. That is to say, they're satisfied by the same object. Now, this doesn't quite get us equivalence for quantifiers, but now we're cooking with gas, because now we can define the notion of substitution of equivalent whiffs. So suppose that P is logically equivalent with Q. Then for any sentence S containing P, SP is satisfied just in case SQ is satisfied. And so we can substitute one or the other just so long as the two are logically equivalent. So this justifies what we did with our quantifiers above. Recall that we turned out a bunch of equivalences like the following. Because these two subformulas are equivalent, like P and Q, the substitution of one for the other renders a sentence which is true under the exact same conditions. And so we can turn out as many of these as we please using the same principle. For instance, for every x, x isn't an f or it's not a g, which turns on our rule for double negation here. Or for every x, it's not the case that x is an f and x is not a g, which, as we can see if we push the negation through, will just give us the following, where we flip the conjunction sign and double negate the g, which of course is just a repetition of this sentence up here. So you can keep on doing this as long as you please, and all of these will be equivalent based on our notion of the substitution of equivalent whiffs. Now, these sentences are not tautologically equivalent, but they are FO equivalent. And their FO equivalence turns on our extension of the notion of satisfaction to deal with these subformulas, which we can treat as equivalent, just in case they're satisfiable under exactly the same conditions. Now we're going to wrap this video up with a very important notion that's going to be with us for the remainder of the course, and this is the De Morgan equivalences for quantifiers. Now you'll recall that the original De Morgan's laws governed the operation of Boolean operators, and they gave us such equivalences as not A and B is equivalent with not A or not B. And this is all well and good for the Boolean operators, but there's a further way we can extend this notion to the quantifiers. Here's the basic idea. For all x naught is equivalent with not some x, and not all x is equivalent with some x naught. We can say everyone did not buy a pineapple is equivalent with not someone brought a pineapple, no one brought a pineapple. I said that these would be natural language equivalences, but not someone brought a pineapple might be a bit much. The point is that these two are equivalent, and they correspond with this top line of our De Morgan's equivalences right here. Similarly, we can give an equivalence for the bottom line. For instance, not all birds are crows is equivalent with some birds aren't crows, and this just corresponds with this line here. So much then for the intuitive idea, but there's more to be said about these quantifier De Morgan's laws in terms of the notions of conjunction, disjunction, and negation that we saw in the original De Morgan's laws. Here's what I mean. Notice that for all x, fx, every x is an f, is equivalent with a conjunctive string applying x to every constant for every item in our domain. We've seen that we can use numerical subscripts, so we'll never run out of constants. Take, for example, the predicate f to be object. So what this side says is that everything is an object. Well, suppose each thing gets a name, and we affirm that it's an object. So that's going to get us this conjunctive string here. So we'll say this table's an object, this book is an object, this set is an object, and we're going to go this way all the way down until we've exhausted our domain. Well, that's just going to be equivalent with this statement, everything is an F, everything is an object. And similarly, the existential something is F is equivalent with a disjunctive string, which is true just in case one of its disjuncts is true. So just in case one of the items in our domain is F. So universal sentences are equivalent with conjunctive strings, and existential sentences are equivalent with disjunctive strings. And we've already seen how these behave under De Morgan's. So suppose I wanted to negate this top conjunctive string here. Well, I'd put brackets around it, and I'd put a negation sign on the outside. But by De Morgan's laws, this is equivalent with a negation of each of the sentences contained in it, and all of these signs, these conjunctive signs, will flip. So we'll say A's not an F, or B's not an F, or C's not an F, and this will come out true just in case at least one item in our domain is not an F. And this gives us the general notion that it takes only one counterexample, one counter instance to render a universal claim false. If we wanted to do the same on the bottom here with the existential, we would get the following, a conjunctive string of negative sentences. Now notice something. This negation of not all is equivalent with some not, that is to say at least one not, so that this sentence here is an instance of this bottom equivalence, not all is equivalent with some not. And likewise, for all not is equivalent with not some, which gets us this equivalence, albeit in a different order. So we can see then that by the De Morgan's laws, plus reading our universal and existential quantifiers as equivalent with conjunctive and disjunctive strings, we can get these De Morgan equivalences whereby sentences like everyone did not buy a pineapple is equivalent with not someone or no one bought a pineapple, and not all birds are crows is equivalent with some birds aren't crows. And these are our De Morgan's laws for our quantifiers, and that's where we're going to end.